So in the last lesson, we talked about adding matrices, subtracting matrices, and multiplying a matrix just by a number, which we call the scalar. So what we're going to be doing today is learning how to multiply a matrix by a whole other matrix. So let me give you kind of the rundown at the beginning in when we're allowed to multiply matrices and when we're not, because we had rules like that for adding and subtracting, when you were allowed to add two matrices together and when you were not, and we've got rules as well for when you're allowed to multiply matrices. So you can multiply two matrices, let's call them A and B. So you can only multiply A times B if, only if, the number of columns in A, so let's write this, let's say the number of columns A, so let's do m times n. So remember, this is m rows, n columns. We can only do this if the number of columns in A is equal to the number of rows in B. So it doesn't matter what this number is, doesn't matter what this number is, we are only allowed to multiply them together if these two are the same number. So if those two are the same number, then we're allowed to multiply them together. So then what happens is when you multiply them together, the resulting matrix has this as its dimensions. So then the new dimensions of the product matrix end up being m times p. So if we multiply matrix A times matrix B, first of all, we're only allowed to do that if the number of columns in A matches up with the number of rows in B, and what we get is a new matrix. We call it AB, and the size of matrix AB is m times p, the number of rows in A, the number of columns in B. And so that probably doesn't make a whole lot of sense right now, but we need to get that rule down whether we are or are not allowed to multiply them together. So we've got these first two practice examples just to see if the product even works, if we're allowed to multiply them together or not. So this first one, this is teeny tiny on the screen, but hopefully you guys can see it okay on your notes. Oops. All right, so A is a 4 by 6 matrix, 4 rows, 6 columns. B is a 6 by 2 matrix, 6 rows, 2 columns. So 6, the number of columns over here, is the same as the number of rows over here. That means the matrix product is defined. So yes it is. So let's just start with A, yes, and then since it is defined, state the dimensions of the product. The product matrix is going to have 4 rows, just like matrix A does, and it's going to have 2 columns, just like matrix B. So it is a 4 by 2 matrix. And like I said, we will learn in just a moment how to actually multiply them together. This next one, A is a 3 by 2 matrix, 3 rows, 2 columns. B is also a 3 by 2 matrix, 3 rows, 2 columns. The number of columns here does not match up with the number of rows here, so this is not defined. The product is not defined. Okay, now the actual process of multiplying matrices. So I am going to try to write it as the most condensed way possible. What ends up happening is what I do with the matrix A times B is I've got, a 4 by 2 as a result. So each position, what I end up getting, so each position in AB is the row in A multiplied by the column in B. Okay, so maybe, probably, that doesn't make a lot of sense when it's just written out the way it is, but each new position in AB is the row in A times the column in B. So let me walk you through this. So we want to find the product U times V, so here's U. That is a 2 by 2 matrix. It's got 2 rows, 2 columns. V is also a 2 by 2 matrix. If the dimensions are the same, rows and columns, it's called a square matrix. So this is a 2 by 2 square matrix, this is a 2 by 2 square matrix. So the number of columns in U is the same as the number of rows in V. Those match up, so we're allowed to multiply them. The new dimensions will be the outside numbers. So UV is also going to be a 2 by 2 matrix. Okay, so let's set up each spot here. So now I've got 4 spots. Remember the way when we did matrices in the last lesson, how we actually labeled everything? So this is, we use lowercase letters UV. This is UV11, first row, first column. This is UV12, first row, second column. This is UV21, second row, first column. And this is UV22, second row, second column. So they all have this notation that we use when we're talking about what element. So when I said each position, that means each element in AB is the row in A multiplied by the column in B. So for example, position 1, 1, we use row 1 in U and we use column 1 in V. For 2, 1, we use row 2 in U and column 1 in V. So we always use the rows in U, we always use the columns in V. So let's kind of walk our way through this. So let's color coordinate to see if that will help us at all. So I've got a number of different colors. So for our first position, to find this first position right here, I'm going to use purple. So we are going to use the first row in U, and we are going to use the first column in V. All right, so we're going to start ourselves off there. So let's work on our product matrix right here. So U times V. Set up a big space right here. So what I do is I kind of match up each one. I have a 5 and a 9. Here I have a 2 and a 6. So I'm going to multiply the 5 times the 2 and then add to that the 9 times the 6. Oops, I meant to color coordinate. Sorry, this is supposed to be in purple. Let's just pretend that that was in purple. Next spot. So now to move over here. This is position 1, 2. So I'm going to stick with the first row. So I'm going to stick with the first row, but now I'm over in the second column. All right, so first row, second column. So I pair up the 5 with the 1. So I multiply 5 times -1. And then I add to that, I pair up the 9 with the -5. Okay, so that's my next spot. Okay, so let's close this off. Now I'm going to go down into the second row. So in the second row, I want to be in the second row in the first column. So back in my original matrices, I use the second row and I use the first column over here. All right, so pair these up just like I did in the previous ones. -3 times +2. And then I combine that with a -2 times a +6. Okay, I'm going to add those up. Last spot, 2, 2. So I use the second row over here with the second column over here. So I pair them up together. So -3 times -1. And then combined with -2 times -5. Okay, so now I'm going to start simplifying everything up to get my answer. So equals. So 5 times 2 is 10. 9 times 6 is 54. So 10 and 54 gives me 64 for that spot that was supposed to be in purple. Then move over here. 5 times -1 is -5. 9 times -5 is -45. So -5, -45, that gives me a -50. Next spot, here I get a -6, this is a -12, -6, -12, it's a -18, and my last spot, -3 times -1 is +1, -2 times -5 is +10, so I'm sorry, +3, +3, +10, it's a +13. So there are all my spots. I can close off my bracket. That is my product. So that is my final answer, the product U times V. All right, so these are definitely tricky problems, so let's be nice and careful as we're going through the other ones. So real world example, we want to multiply some matrices. So we've got the matrices below. Use matrix multiplication to determine in which season Lisa Leslie scored the most points. So this is Lisa Leslie's regular season scoring. We've got years, 2005, 6, 8, and 9. I guess we skipped there. Field goals, 3 points, and free throws. So when we combine everything up, so here are the number of baskets that she made. So here are all the field goals right here in different years. Here are all the 3-point field goals right here in different years, and all the free throws in different years. So we are going to multiply those by the point values because each field goal is worth 2, each 3-point field goal is obviously worth 3, and then each free throw is worth 1 point. So this matrix right here is a 1, 2, 3 by 4, 2, 3, 4. This one right here is a 1 by 3. Okay, so looking at them the way we are not allowed to multiply them together because the 1 times 4, those don't match up. But let's say I switch the order, multiplied P in front of B, then these would match up. All right, so I am going to multiply P times B, because that way I have a 1 times 3 times a 3 by 4, and then the rows and columns would match up just like they're supposed to. All right, so let's work through this one. So if I do P times B, if I switch these, that is a 1 by 3 times a 3 by 4. So these numbers match up, which means my new product is going to be a 1 by 4 matrix. So P times B will be a 1 by 4 matrix. Okay, so let's get that set up. So P times B is going to be a 1 by 4 matrix. So I'm going to have one spot right here, 2, 3, 4. Leaving lots of blank space because I know I'm going to be doing some multiplying. So 4 spots here. So let's work our way through this. So the first thing I do, there's only one row. So on the right hand side, I'm always multiplying this one row times whatever column I choose. So first I'm going to multiply that one row by that first column. So I multiply 197 times 2. And then 7 times 3. And then 102 times 1. So what this one represents, these are her points in 2005, because for each of her 197 field goals, she got 2 points. For each of her 7 3-points, she got 3 points. And for each of her 102 free throws, she got 1 point. So when I combine these all up, I'm going to get the number of points that she scored in 2005. And then I'm going to do the same thing for 2006. So I'm going to multiply these 3 values by these 3 values, match them up and multiply them. So 249 times 2 plus 8 times 3 plus 158 times 1. Okay, move it on over to the right, the next year, 2008. We're multiplying this column times this row, so 2 times 184 plus 3 times 4 plus 117 times 1. All right, and then finally, move to my last column right here. This column represents her points in 2009, and then again, times this row. So 2 times 143 combined with 1 times 3 combined with 65 times 1. Okay, so now all of those values, we're going to add them together. So I am just going to use a calculator, of course. We don't want to deal with trying to do any of that stuff by hand or in our heads or whatever. So let me get you these new values here. Oops, there we go. Okay, so for this first one, we've got 197 times 2 plus 7 times 3 plus 102 times 1. So 517 points for that first season, 2005. So for my first column, I've got 517. Okay, then let's move over to the next spot. Next spot, I have 249 times 2 plus 8 times 3 plus 158 times 1. Okay, so for that next year, I get, oops, that is not showing up very clearly, is it? There we go. 680 for the next year. Next, I've got, let's get it so we can see that. There we go. Okay, so I have 184 times 2 plus 4 times 3 plus 117 times 1. 497. That's for 2008. Okay, and the last one. 143 times 2 plus 1 times 3 plus 65 times 1. 354. She's slipping a little bit. Okay, so that was my last one. So this is my final matrix. How many points did she score each season? So we've got the total number of points for each season by multiplying by this point matrix. All right, so now let's flip over, take a look at some properties that we've got. Multiplicative properties. We talked about the additive properties. So we are going to determine if the commutative property holds for these two matrices. The commutative property tells us that we can multiply A times B or B times A, and it doesn't matter. So let's start by attempting to multiply A times B. Okay, so A times B, remember what we're going to do is line up the rows with the columns. So first, we're going to multiply this row times this column. Same thing we did before, line everything up nice and neat. So we do 4 times negative 3. So 4 times negative 3 gives us negative 12. And then we're going to combine that with negative 1 times negative 4, and that gives us 4. All right, so next I move over into this spot. So I'm still in the first row, but now I'm in the second column. So I still use the first row right here, but now I'm in the second column. All right, so I line these up and multiply them. So 4 times 6 is 24, combined with negative 1 times 5, which is a negative 5. Okay, so close that off because I know that's the end of my columns. Now I move down here, now I'm in the second row, first column. So I am going to use the second row in my left matrix and the first column in my right matrix. So line them up. So 5 times negative 3 is negative 15, plus negative 2 times negative 4 is a positive 8. And lastly, second row, second column. So on the left, I am going to use the second row. On the right, I am going to use the second column. Match them up and multiply them. So 5 times 6 is 30, plus negative 2 times 5 is a negative 10. So let's combine up all of those values into my new matrix, AB. So equals, let's get everything all set up in here. So negative 12 and positive 4 gives me a negative 8. Positive 24 and a negative 5 gives me a positive 19. Negative 15 and positive 8 gives me negative 7. And 30 and negative 10 gives me 20. So that's my matrix AB. What we're going to try to figure out is if AB is the same as BA. AKA, can I multiply them in a different order, and will it matter? So we are going to rewrite our two matrices so I don't get my circling all confused. Just to keep us organized up here. I already circled a lot of things and used a lot of colors, so let's just rewrite them. So we want B to be on the left and then A. So whichever matrix is on the left, you organize in rows, just like we did here. Whichever matrix is on the right, we organize in columns. So we are going to start to set up this matrix to see if they come out to be the same. So for this first spot, I'm in the first row, first column. So I use the first row of A, and I use the first column, the first row of B and the first column of A because I switched the order that I'm multiplying in. So I start with negative 3 times 4, and I get negative 12, combined with 6 times 5, and that's 30. For my next spot, I'm still in the first row, but I move to the second column. So I still use the first row here, but I move to the second column here. So I match them up again. Negative 3 times negative 1 is a positive 3. Combine that with 6 times negative 2, that's negative 12. So close this off because there are no more columns. Now into the second row. Second row, first column. So I use the second row of my first matrix. I use the first column of my second matrix. Match them up. Negative 4 times positive 4 is a negative 16. Combined with 5 times 5 is 25. Next, I'm in the second row, second column. So I'm going to use the second row of my first matrix, the second column of my second matrix. So line them up. Negative 4 times negative 1 is a positive 4. 5 times a negative 2 is a negative 10. So combine these up. Hopefully we have probably noticed that these do not turn out to be the same. We're going to write our answer anyways. So negative 12 plus 30 is a positive 18. 3 plus a negative 12 is a negative 9. Negative 16 and 25 gives me 9. Oops, red. And 4 and negative 10 gives me a negative 6. So hopefully it is definitely clear that AB does not turn out to be the same as BA. So the commutative property for most examples will not hold for multiplying matrices. So it is not true that AB is equal to BA. That means the commutative property does not hold for matrix multiplication. The order that you're going to multiply the matrices in is very, very important because it will determine how your answer turns out. All right, example 5, we're going to see if the distributive property holds. So we've got R, S, and T. We want to see if S plus T times R is the same as S times R plus T times R. So a little bit more matrix multiplication here just to practice. So with this one, order of operations says we start with S plus T. So let's start with S plus T. So we are taking matrix S, matrix T, adding them together, which means combining up all their values. So for my first value, I add the 4 and the negative 3, and I get 1. Then I add the 6 and the 7, and I get 13. I add the negative 2 and the negative 4, and I get negative 6. And then I add the 5 and 8, and I get 13 again. So that is my new matrix, S plus T. So what I then want to do, according to this, is I want to multiply it by R. So let's multiply it by R. Okay, so same exact process as I've done in all the examples up above. When I come up with my new matrix, notice these two are the exact same size, which means I can multiply them together. So I start in this spot right here. First row, first column. 1 times 2 is 2. 13 times 1 is 13. Then I move over to this spot. So I am still in the first row, but now I'm in the second column. 1 times negative 1 is negative 1. 13 times 3 is 39. Okay, now I move down here. So now in this matrix, my new matrix, I'm in the second row back to the first column. So just like the other ones, match them up and multiply. So negative 6 times 2 is a negative 12. 13 times 1 is 13. And last one, I am still in the second row. I have moved over to the second column. Negative 6 times negative 1 is a positive 6. 13 times 3 is a 39. So let's combine these up to get our answer. So 2 and 13, that gives me 15. Over to the right here, negative 1 and 39 gives me 38. Down in the second row, negative 12 and 13, that gives me 1. And 6 and 39, that gives me 45. So this is what I get for my left-hand side here. If I add the S and T first, and then multiply by 4. We want to see if distributing, not 4, R. We want to see if distributing the R first actually holds. So let's do S times R, then we'll do T times R, and then we will see if adding them together comes out to be the same as this matrix up here. So S times R, let me write those out. So there's S, and then times R. Okay, so I'm hoping that we are getting used to this process by now. So let me write out our new matrix. So starting with the first row, first column. Match them up. 4 times 2 is 8. 6 times 1 is 6. Next spot, we are still in the first row, second column. So first row, second column. 4 times negative 1 is negative 4. 6 times 3 is 18. Now we move down into the second row. We're back to the first column. So second row, first column. 2 times negative 2 is negative 4. 5 times 1 is 5. And the last spot in this new matrix is the second row, second column. So I use the second row here, second column here. Negative 2 times negative 1 is positive 2. 5 times 3 is 15. So let's combine these up, see what we get. 8 and 6 gives me 14. Negative 4 and 18 also gives me 14. Negative 4 and 5 gives me 1. And 2 and 15 gives me 17. So it's not supposed to match up yet. I still got to do this multiplication and see what I get when I add them. Okay, so T times R, here's T. and then times r. Okay, so we're going to do the exact same matrix multiplication one last time. See what we get. So, first spot, it's the first row, first column. Negative 3 times 2 is negative 6. 7 and 1 is 7. Next spot right here, first row, second column. Negative 3 times negative 1 is 3. 7 times 3 is 21. Down to the second row. So now I'm in the second row, back to the first column. Negative 4 times 2 is negative 8. 8 times 1 is 8. And my last spot in this matrix, I'm in the second row, second column. So I use the second row here, second column here. Negative 4 times negative 1 is 4. 8 and 3 is 24. So combine those up, and then for our last step, we will add them together. So negative 6 and 7 gives me 1. 3 and 21 gives me 24. Negative 8 and 8 gives me 0. And 4 and 24 gives me 28. So as a last step, I'm going to take these two matrices that I just came up with. So I want SR, which is right here. And I want to add that to TR, which is right here. Okay, so remember the way that addition works from the other day is we add each matching element together. So 14 plus 1 gives me 15. 14 plus 24 gives me 38. 1 plus 0 gives me 1. And 17 plus 28 gives me 45. Okay, so what we were trying to see is if this equals this. So when I did this, I ended up with this matrix right here. When I did this, a couple steps later, I ended up with this matrix right here. So yes, the distributive property does hold, unlike the commutative property, which did not. So finally, last thing we're going to write down very quickly, because I'm sorry this one went a little long. Properties of matrix multiplication. These are the ones that hold. Turns out also that the associative property holds. So two associative properties. The associative property of multiplication, as well as the associative property of scalar multiplication. So basically, that constant can go anywhere you want, and it's not going to change anything. And then we've got the left distributive property and the right distributive property. So left distributive is if we try to put a new matrix on the lefts. It comes out like this. Right distributive is if we try to put a new matrix on the rights. And it comes out like this. Keep in mind that we do actually need these two separate properties because left multiplication, as we learned, is different from right multiplication. You can just take a look at example 4 for that. So again, I apologize for being a few minutes over what I said, but that is the end.